Hi, am I audible?
Yes, you are.
Okay, thank you. So should we start then?
You can wait a couple of minutes.
Yeah, okay.
बीओबी से नहीं हो रहा है।
यहाँ पे नहीं गया क्या वो एयरलाइन थोड़ा बंद करना है और वॉशरूम है ओटी से वापस आए और एक्सटेंडिंग हो गया अच्छा ये बड़ा देखो हमारा और नहीं फोन में देख रहा है
Okay. Now we may start, right? It's already some 7 minutes. So let me see how to, whether I can record it. Okay. I don't think I can record it. Venkatesh, can you record it? I mean, if it is needed.
Yes, Fahad, you can start, I think.
Do we need to record it? Then I cannot do it. Okay. Because
I think there is Gayatri who should be recording it.
okay, because I'm not co-host or something.
Oh, I see. Okay,
I mean,
should I? I've not done it. I can record it. Should I? Let me try.
but yeah, but to do have a provision.
No, I don't.
Okay, so
Let me call Sakit.
okay. Okay, so it will be recorded in the live streaming. That's what it is taught. Okay. So let us start then. Okay, I will be talking about three problems. One is mode, and the other is majority, and the third one is heavy hitters. And all these problems are more or less, very related. Okay, and let us follow the first lecture strategy. Like if you don't understand, you just write a -1. You are also feel free to unmute and say things like if you want me to explain something more. And so here is the outline of the talk. So we will be talking about the three problems. One is mod, and the second is majority, and third is heavy hitters. Okay, what is the mod problem? Okay, given an array of m integers, and I want to find one of the most frequent element in the array. For example, suppose I have 2, 2, 1, 3, 1, 1, then the output of my algorithm should be 1 because 1 occur most number of times. Okay? And suppose I have one more 2 here, then the output can be either 1 or 2. Okay, because both of them are most frequent element. Okay, that is the mod problem. And in the majority problem, it is same as mod where the frequent element should appear more than half of the time. Okay, and then there will be only one such element if because you cannot have two elements that appear more than half of the time. So the majority is a special case of mod where there is only one frequent element and that should appear more than m by 2 times. Okay. And the third problem, which is like heavy hitters. And so the input is an array of m integers and a small parameter k. And we want to output all the elements which occur more than m by k times. So if the frequency of an element is more than m by k, then we should output it. Okay. How many such elements will be there? There will be at most k such elements. Okay. So the heavy hitters problem, we need to output all the elements whose frequency is more than some number m by k. And what is a just one simple solution for like this problem? How do we solve about it? One simple algorithm to solve it.
Sorting.
Yeah, sorting, right? You just do sort the numbers, okay, and then you do scan the sorted list from left to right, and within that scan you will be able to compute all these things. Okay, and now as you all know that sorting, any sorting algorithm, comparison based sorting algorithm should take more than n log n comparisons. So it will take, so if we are going to use sorting, then it will take n log n comparisons. Okay, and then one natural question we could ask is like, okay, can we reduce the running time? Or like running time is related to the number of comparisons if I use a comparison based combinatorial algorithm. So can we reduce the number of comparisons? And the second disadvantage of doing sorting is, okay, either I need to alter the input array because I need to store these sorted elements. So either use an additional array where I store all these sorted elements, or I just change the input array itself and make it sorted. Okay, so I need to do one of those, right? Either I need to change the input array, and or I need to use, like if I'm not allowed to change the input array, say for example the input array is just read only, then I have to use an additional array of length m. Okay, so the sorting based so solving this problem using sorting will have these two disadvantages. Okay, now next we will see how to find mode of a list of elements in less than n log n comparisons. Okay, so next we will see like an algorithm for finding mode with less than n n log n comparisons. So this is the objective. Suppose the the most frequent element appear, like the frequency of the most frequent element is f, then in the algorithm which we will see in the next slide, the number of comparison we will be using is, okay, so here, forgive me, this is m log m. Okay, so I use the m is number of elements. Algorithm uses or m by it's going a bit slow. Okay, yeah. So next, my objective is to,
sir,
yeah.
What is m there?
M is the length of the array. M elements are there in, here it is. Given m elements. So this algorithm is by Dobkin and Munro. And so the idea is follow the quicksort algorithm where we stop at an intermediate step. Okay. Now let's see the algorithm. A subset of A. Okay. And a block is called homogeneous if a block is said. Okay. And otherwise it is called heterogeneous. And then what we do is, initially we will have one block which is A. If it is homogeneous, which means that all the elements in the array A are same, then you just output that element. Otherwise what you do is, this is like in intermediate steps you will have many blocks. Okay, among all the blocks you pick the largest block. Okay, and you check whether it is a homogeneous block. If yes, then you output the only element in that block. Otherwise what you do is, you do the idea of the quicksort step you do there. Okay, you find the median element x in B. Okay, what is a median? Okay, median is like if you sort the elements in B, what comes in the middle, and that is called median. Okay, a median of a set of numbers is like if you sort that set of numbers and what comes in the middle, that is called the median. Okay, if the number of numbers is odd, that middle is well defined. Otherwise there will be two middle numbers, any one of them is called a median. And now after finding the median, what you do is, you will create from block B, you create 3 blocks. One is all the elements which are like equal to x, and the other block contains the elements which are less than x, and the other one is the elements that contain whose value is more than x. Okay, you continue this process. Okay, and this is the algorithm. Okay, and you can see that this is a modification of quicksort, where at some point you will be saying like you will be using this step, output an element if from a homogeneous block, and if that block is the largest block. Okay, let's see a simple example and then we analyze its correctness. Suppose we have like say 2 1 3 1 3 4 3. So 3 is the answer, right? So initially my array is like this. Okay, now what will be the median of this? It will be like, if I write in a sorted order, 1 1 2 3 3 3 and then 4. So the median will be 3, right? So now I will construct 3 blocks from it, and this contain how many 3s? Like there are 3 3s, okay, which is equal to, and this side it will be 1 1 and 2. And this side it is just one element 4. Okay. And then in the second step, I will pick one of the largest blocks. Oh, that could be this 1, 1, 2. And in 1, 1, 2, the median is 1. So we will be making, 3 blocks, which is 1, 1, and then 2. And the other block is empty. So if it is empty, then just leave it. Okay. And now these are the blocks. And now look at which is the largest block. And you will see that, okay, oh, this is the largest block. And what you will output is like, and that is homogeneous, and you output the element in it. Okay. Now, okay, clearly the algorithm is correct, because at any point in time, look at the numbers, right? Every element, there will be some block which is homogeneous, and then that is the largest compared with all other blocks. And this block is this block, uh, uh, this block, all the elements are same, and there will be no two blocks where, I have a same element. Say I cannot have two blocks where X is appearing here as well as X is appearing here. That's not possible. So if I have an element X, then from the second, step on, like from the first step, at any step, X will be in the same block. Okay. Because of that, what the algorithm output is always correct. Okay. Now, now let us see why I use only order m log m by f comparisons. Okay. Now, you can see this as a recursive tree. Okay. So how does it work? Like I have an array, and from that array, compute a median, and then we will be making 3 subarrays, right? And each of these, left, right, and everything, and this will have size at most half of this. Okay. And maybe this will have more than half. If this will have more than half, then at that point, we will be stopping, because this element contain the mode. Okay. So these two elements, the number of elements in the left as well as the right, we will have like at most half of the first one. Okay. So and any block, when we stop, what will be its size? Its size is at least m by 2, right? Because if it's, oh sorry, f by 2. If f is the frequency of the most frequent element, then when I stop, the block size will be at least f by 2. Okay. Then if that is the case, then what will be the depth of this tree? Like, so like you can visualize it like a tree, right? Initially I have a here, and then I split into 3, and then pick the largest block in it. If it is homogeneous, output, that element. Otherwise, you make it 3, and then continue this. And what will be the, like, this forms a tree. And what will be the depth of this tree? Did you understand the algorithm? Okay, good. Is it f by 2? The size of the block when I stop, every block will have size at least f by 2. Right? That is right. That is the block size. I'm asking about the depth of the tree. Okay. Will there be any?
Sir?
Yeah. Yeah.
Sir, from the first array, do we always split it into 3 parts?
Okay. So one of them may be empty.
No, like sir, I didn't understood the extrapolation which you did, the tree from first array to like on the slide above. Huh,
Okay.
here. So here
Okay.
you did into three part, but the
Yeah.
first one part you split into only two. It could be one can be in one block, one can be in one block, and then two can be in other block. This can also happen, right?
That is not the algorithm, right? Look at the algorithm doing.
Hmm.
Pick the largest block. Initially, I have only one block. So the largest block is the same block that is containing all the elements A. Okay. And
Okay.
we will check whether it is homogeneous. If it is, we output the element. So that is not a homogeneous. Okay. Now you find the median in that block. Okay. So that block B is actually equal to A. So you find the median, and the median is actually 3. Now you are
Yes.
going to, you know, replace this block with 3 other blocks, which will, their union will be same as the elements of that block. And that is equal to that element and something less than that element and the elements which contain more than that element. If the elements are there, say, okay, what is the question? What if all the elements are same? Yeah, what if all the elements are same? A contain all the elements, they are same. A is the largest block, and you check whether it is homogeneous. Homogeneous means all the elements are same. Output that element and stop. Like output means output and stop, nothing. And if all the element, the output the element. Yes, it's an answer to that question. Okay. Now, 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 this forms a tree-like structure. And what is the depth of the tree? Notice that the middle guy, the middle block, it will not have any children because that is a homogeneous block. So either we will be hitting the right block or like we will be splitting maybe the left block as well as the right block, at different stages. Okay, so it will form a tree-like structure. Okay, and because the most frequent element is uh, 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 most frequent the frequency of the most frequent element is f. you know I will not be splitting a block whose frequency is less than f. So I may be splitting a block whose frequency is more than f. Because of that, every block when I stop my algorithm will have size at least f by 2. Okay, and what is the question is, what will be the depth of this tree? Now what I can say is the depth of the tree will be log m by f by 2. Okay, why it is so? What will be the size of this and this? This is at most the size of this by 2. Like size of, say, suppose the size of this is m prime, then the size of this block will be at most m prime by 2, and this block will be at most m prime by 2. Okay, so as we go from one level to the other, the number of elements in the block reduces by a factor of half. Okay, and the middle guy may become homogeneous. If it become homogeneous, then there is no further going down from that block. Okay, so and after we do k levels, like then the size of the block in the leaf level will be m divided by 2 to the power k. And we know that this is like what is m divided by f by 2, right? It is at least this much. Okay, and this implies that
Sir, I understood m divided by 2k, but that would just mean log m, right? How do we infer m divided by
yeah
f?
yeah, let's see, m divided by 2 to the k, so will be the size after I go k steps.
Yeah.
Okay, and this will be what is that this value is at least f by 2, sorry, not m by f by 2, because in the leaf node every uh, every block has size at least f by 2. Okay, and the depth is k. This implies what is k? K is less than or equal to log 2m divided by f. Is that clear?
Yeah, it makes sense. But how did we infer that every block would always be greater than or equal to f by 2? I'm sorry.
Okay. Yeah, sure. Let's go. Okay, suppose the most the frequency of the most frequent element is f. Okay, now I will be doing the splitting of b only if its frequency is more than or equal to f, right?
Okay, I get it. Thank you.
Okay, so if it go be less than f, then you will not be doing that splitting.
Thank you.
Okay, so the depth of this tree is log m, so the depth of the tree is log m 2m by f. Okay, now how many comparisons I will be doing is depending on how to compute the mode, the median. Okay, now there is an algorithm to compute median using order m comparison. Like the median of m elements can be computed in time order m or using order m comparison. Okay, this means that here I will be doing order m comparison. Here I will be doing order of what is the size of this, that many comparison to compute the median. Here also I will be doing order of what is the size of this block, that many comparison. So in every level, like if I look into this is the first level and this is the second level, I will be doing total order m comparison. And the number of levels is equal to the number of the depth of the tree, and that is log 2m by f, and hence we will be doing, order of m log 2m by f comparisons. So suppose the frequency of the most frequent element is m by 3. And any question? Okay, so we will be doing order m comparison per level, and the number of level is log 2m by f. So order m log 2m by f comparison. Suppose f is m by 3, then it will be doing order m comparison. So it is much faster than what we do according to the sorting based algorithm. It is essentially doing quick sort, but stopping at some intermediate step. So this is what I want to talk about, the mode finding algorithm, and using less number of comparison than blindly doing sorting. Next, we will move to the following problem, the majority element. So there is an array that contains m elements, okay, m integers, and some of them may be repeating, and we want to output if there is an element which occur strictly more than m by 2 times. Okay, and if such an element occur, then there will be exactly one such element, and I want to output that. Okay, how to do it, and what is the number of comparison we need to do it?
If we use the same algorithm, then f is m by 2, so it becomes order m time.
Comparison, yeah, correct. Okay, so if you do the same algorithm, you can get it in order m comparison. Okay, use the mode finding algorithm, and the number of comparison is order m. Okay, now here is the point. Okay, either I need to come up with use additional space, which is the space for all the blocks, or I can reuse the input array where I need to alter that. Like I need to keep blocks in the same input array. And if I'm not allowed to change my input, then I have to use additional space. So that additional space is, at least, omega n, omega m. Okay? So suppose I don't want to use this much space. Okay. And we are going to see in an algorithm that uses only two additional registers. Two additional registers, each of them can store a number between 1 and m, which means that, in terms of bits, using at most 2 log m more bits, without changing my input array, we are going to compute the majority element. Okay, that is what the next is. So here is that algorithm. Okay, what we do is as follows. The algorithm will have a counter, which is C. Okay, initially that counter is 0. And we will have a variable S, and initially that is null. You think that algorithm is going to keep a potential majority element in S, a potential majority element. Okay, so it goes and look for the first element in the array, which is A1. And then what it says is like, okay, pretend that is the majority element. Okay, then the counter value is 1. Okay, and then if that element comes again, then you are going to increment the counter. If some other element comes, then you are going to decrement the counter. Okay, and if at some point the counter value is 0 and you are going to get a new element, like in the array, you just pass to the next element, and at that point the counter value is 0, then the algorithm does the following. Algorithm makes a correction. Okay, algorithm say that, okay, maybe what I stored in S is not the correct candidate, so just forget about that element and pick the next element being the potential candidate for the majority element. So do this process, and at the end, the algorithm will have two values. S is a potential candidate for the majority element, and C is some counter value. Okay, and then after doing this one, what the algorithm does is check whether S, which algorithm finally found, is actually a majority element. How can you check it? You just check how many times S occur in your input. Just passing your array from left to right and counting the number of times S occur. Okay? And if it is more than m by 2, you output S. Otherwise, you say that there is no majority element. Okay, let's see an example. Then things will be clear. Okay. Suppose we have like 2, 1, sorry, 2, 2, 1, 1, 3, 4, 3, 3. Which is the majority in this one? Okay, so there is no majority element. 1, 2, 3, 4, 5, 6, 7, 8. So maybe like, let me change it. This is okay. Now 1, 2, 3, 4. 1, 2, 3, 4. Okay, like I need one more, right? Okay. So now here the majority element is 3. Okay. Now, so this is the input array. And how does the value is, and the counter C changes when we move from 1 to m. Initially, when I is equal to 1, you will say that, okay, the first element, that is my S value, and then the counter will be 1, and then you will see like again you will see the element, which is the second element, that is same as the value stored in S. So what you will do, you will increment the counter. Okay, the counter value will be, this is the counter value. Okay, this is not an array. Okay, how does the counter changes? This is not an array. How the counter changes. Okay, and so you will not be, the algorithm is not will not be changing the value in S. And then the next element, which is 1, at that time, at that 1 is not equal to what is stored in S. So what it does, and the counter value at that point is time is 2, which is more than 0. So you will decrement the counter by 1, and S won't change. And next, the next element, which is actually the majority element, okay, which is 3, comes, and at that time, the counter value is more than 0. So you just decrement by 1, and then you store here 2. Okay, and the next element comes, which is again 3. So what you will be doing is, the counter value is 0, and S is not equal to 3. So what you do is, you just change counter to 1, and the S is 3. And look at the next element. The next element is 4. Okay, and 4 is not equal to 3, and the counter value is 1. So S is actually 3, and this is 0. And the next element, 3, which is same as what is stored in S. So what you will, S is 3 itself, and the counter is 1. And here, and in the next iteration, again 3 comes, which is equal to S, and the counter increments to 2. And the next step, again 3 comes. So the counter value here will be 3, and S will be 3. And at the end, what the algorithm does, okay, algorithm got 3, and it will verify whether it is indeed the majority element. For that, you just go through the array once again from left to right, and count how many times 3 occur. And if it is more than m by 2, you will output that element. Okay, is the algorithm clear?
Yes. Sir, I have a question.
Yeah.
So the fact that we are checking in the end that if it is a majority element, does that mean that that our S variable always holds the mode, basically?
The point is, like, suppose there is no.
I understand. I'm sorry. So if we have an example such as 1, 2, 3, if we have that list, then the 3 would automatically be chosen as the majority, and that is really the majority element, though. That's why we're doing the check. I understand.
Yes, that's.
But
that's
does this? So if we do not do the check, does this mean that 3, like our variable S would always store the mode?
No, it is not.
It's not. Okay.
It is not. Say, for example, you just change this 2, 2, 3, 3, 5. It will be storing 5.
I see.
2,
okay.
2, and then 3, 3, decrement, and 5. Next, it will be taking 5.
That makes sense. Thank you.
Okay, now what we know, okay, now we need to prove that the algorithm is correct. Okay, now how do we prove the algorithm is correct? Okay, now at the end, it will be outputting some value. Yes, and yes, it will be eventually checking. If there is no majority element, it will not be saying there is a majority element and outputting it. That is very easy. And the only thing we need to check is, if there is a majority element, then how is it going to correctly say that what is stored at the end of the algorithm, S value contain that majority element. Okay, so for every element Q in the array, let FQ be the frequency of Q, the number of times Q occur in that array. And let's say maybe I use J here, and then Fj. And suppose suppose there is a majority element, which is Q. Okay, and then, and we want to, I will claim that, the algorithm output is which is actually equal to Q, and the C value will be at least FQ minus M by 2. Okay. Now to see that proof, just look at this. Okay. Here is the array, the input array. Just closely look at this iteration. Okay. So in the first step algorithm, okay, just to pretend that the first element is the majority element and store it in S. Okay. And it continue to assume that, and at some point it will say like, oh, this is a mistake and I need to choose, you know, some other element, which is that particular AI value. And that could be the majority element. What I have seen so far may not be the majority element. Why? When does what okay, what is the reason for happening that? Because, you know, the first element which the algorithm, you know, will think that, okay, this is the majority element, and then whenever S comes, it increment, and whenever some other element comes, it decrements, and at some point the counter becomes 0, and then when a new element which is not equal to S comes, then it changes its S. Okay, so these are all the places where the change in S happens. Okay, so these are all the places the change in S happens. Okay. Why there is a change in S happened? Just before that, the counter value here was 0, and what the next element, this element, which is not equal to the S value is stored. Okay. Now, if you carefully look, now, how many times this element, let's say call it A1 appear here? A1 will appear half of the times in this first, you know, the marked region, and half of the time some other element appear. Because of that, you know, the counter become non-negative and becomes 0. And that happens from here to here as well. Sorry. Half of the time that was same to, you know, AI2. Okay. And half of the time some other element. And here it is AI3. And from here to here, if you look into, half of the time it is AI3, and the remaining time some other element. Okay. Now, using that fact, if you look into from here to here till this point, maybe till this point, any element can appear at most half of the time. Like in this range, any element can appear at most half of the time in that range. And if I take this range, any element can appear at most half of the time. So in particular, Q will also appear at most half of the time in this range. Okay. And in this range, you know, more than half of the time Q will be appearing. And since I don't have any change in values for S, and the counter will not become negative, this element should be Q. If this element is not Q, then there will be some location where it will be changing to, you know, Q value. Okay. Since there is no change in that after this location, and in this region, I have more than half of the element is Q, this element will be Q, and what my algorithm storing in S at the end of the algorithm is actually Q, and at most half of the time here is Q, which means that the counter value here will be the number of times Q occur in this range, like the range, maybe the range I marked as green. Yeah, this green range, like minus the other element. So that will be more than FQ minus M by 2, because of you just do the calculation, because this side left of it, at most half of the time it is Q, and more than half of the time it is some other element. Okay, and is the proof clear? If not, which argument is not clear? I will explain that. Okay, fine. So what is the space usage? 2 counters, right? Additional space used is 2 counters. So look at the algorithm. Additional 2 counter, like two variable s and s, and each of them will be storing, order m bits. So, order log m bits additional space it uses. And how many comparison it will be doing? It will be doing only order m comparison. Okay, it will be doing only order m comparison. Additional space is order log m bits. If in terms of words, it is order 1, actually 2 words. Now we move on to the last problem. Okay, I have some 10 minutes. Okay, which is the heavy hitters problem. Okay, and the algorithm is a extension of the majority, the computing the majority, which we have seen in the last slide. Okay, just extension of that. Okay, so in the heavy hitters problem, we want to output all the elements that occur more than m by k times. So the input is this array which contain m elements and an integer k. And we want to output all the heavy heavy elements, which are the heavy elements which occur frequently. Like frequently is defined as its frequency is more than m by k. And there will be at most k such elements. And we want to output all of them. Now, so k equal to 2, that's what we have seen for the majority. Okay. Now what we have to do here is we will be keeping, like we do the an extension of what we did for the majority, and that is as follows. I will have k counters. These k counters are d of 1, d of 2, etc. up to d of k. And I will have the potential, like we will be storing a potential majority element, right? That is in S for the majority. Here, like the potential solution set size is could be at most k. So the potential heavy hitters are stored in the array S. Okay. And it is similar to what we did before. Like whenever an element comes, or an element, like when you just parse from left to right, from j equal to 1 to m, what you do is, if there is a counter free, like which is not used, or its value is 0, then you say that, okay, this could be a candidate for me, and I will use that counter for adding when that particular element appears, and store it in S. So for I going from 1 to m, for j going from 1 to m, if a of j equal to s of r for some r, which actually means that the algorithm already made a guess that just a small information, we do not have tutorial. Okay, so there is a message to all. So when a of j equal to s of r is a potential candidate solution, right? And then what you do is the corresponding counter, which is d of r, will be incremented. And then and if that is not the case, a of j is not stored as a potential candidate, but my current set of potential candidate is less than k, which means that I am afford to put one more. Okay, like one more I can store it in S. So I will assume that a of j is that candidate, and I will pick one counter and one one location from this array S and store S of R is equal to that value, and the counter will be 1. Okay. And if that is not the case, then what is happening? If these two are not the case, then there is a potential candidate set which is K, and the counter values is, uh, uh, is not equal to 0. Like counter, there are some counter values, like counter values are non-zero. Okay, then what we do is we are going to decrement all the counter values by 1, and that's it. Okay, and after doing this operation, if any of the counter becomes 0, then what you do is you just throw away that element, because this like algorithm can make a guess that okay, this may not be the potential candidate. Okay, the corresponding element you just throw away from the list S and make it null, and the counter value is just let it be 0. Right? And then next iteration, some other element will come and it will take the position of that S, and you will increment that counter. Okay, and at the end, what the algorithm will do is it is going to check all the elements in S, how many times that element appear in A. If it is more than m by k, then you just output that element. Like, so you will be outputting at most k elements. Is the algorithm clear? Okay. It is an extension of what we did for the majority. If it is not clear, please let me know. I will explain it once again. Okay. So what is the space?
How does R increment? Like in the algorithm, R, how like when do we increment R in the algorithm?
Okay. Suppose like you are in the jth iteration and you look at the element A of j. If A of j is equal to sum of the potential candidate stored in S, then you are going to increment one particular count that is corresponding to that element. Okay, that is here. Or like there is a space free, like you have only stored, like that is not the case. Like A of j is not equal to S of R for any of the counters or any of the potential candidate, but you have kept only less than k potential candidate, then you assume that okay, this new element is a potential candidate, and you will store that in one location in S, which is vacant, and corresponding counter you increment. Is that clear? Okay, can I? Okay. Say maybe like in an example, say k equal to 2, 2, 2, 1, 3, 3. Okay, so maybe I will take 10 more minutes. Okay, like so we will have two counters, right? C of 1 and C of 2, and we will have locations for S of 1, S of 2. What it does, first two come, like first element is 2, and the counter value is, the first counter is 1, and this value is, oh sorry, this value is 2. Next 2 comes, it check whether it is already stored potential candidate. Yes, 2 is a, like when the second, when we are going to process the second 2, like the second element, which is also 2. So you increment this. And when the third time, which is like the third iteration, 1 comes, what you do? Like, okay, 1 is not equal to S of 1, and this value, this is null. Okay, so there is a counter free, there is a potential, there is a location in S free for 1. So 1 here, 1 here. Next comes 3. All the counters are full, S is full, and 3 is not equal to 2, 3 is not equal to 1. What you do? Both the counter decrement 1, 0. Okay. When this becomes 0, what you do? You just, which one? So this will be 2, and here you make it null. Okay, so you are going to throw away 1. And then, so this is what, when the fourth element 3 comes. And then the next element, which is actually 3, comes in. And you will see like there is a 3 is not equal to 2. And 3 can be stored as a potential candidate because there is a vacant space. So what you do? 1 here, 1 here, 2 here, 3 here. Is the algorithm clear now? Okay. So this is the algorithm to it. Okay. Now, how much space additionally it uses? You know, here there is a k-sized array. Here there is a k-sized array, 2k size total. So 2k, and each of them will be storing some numbers. We assume that it is between, like every element is between 1 and m, or and the counters will be going at most m. So it will be using order k log m bits. So now I want to prove its correctness. Okay, to prove the correctness, so for any j, if j is the frequency, okay, the number of times the element j appear in A, in the array A. Okay. Now for each r in k, like f hat of s of r, think that s of r is equal to j, some element, that will be equal to, say, I assume that is equal to d of r, what is my output of the algorithm, like is what is stored in d of r. And yeah, okay, so essentially like f hat of j is equal to d of r if s of r is equal to j. Otherwise, so for k of them, I will be storing some values. For the remaining, I will not be storing any values, so I just assign those values to be 0. Now what we prove is this f hat value, for fix an element I in A, the f hat value, f hat I, is at most fi. Why f hat I is at most fi? That is very easy to see, right? At some point in time, I will be using some delocation counter, and when an element corresponding, when an element I, like I comes in, and later on that counter is incremented only when I comes in, right? I pops up in that iteration. Okay? So which means that the f hat I is at most the frequency of I. And the important thing is we can prove that f hat I is at least fi minus m by k plus 1. And this implies the correctness of the algorithm. Notice that for any I whose frequency is more than m by k, the f hat I value will be positive, and hence the algorithm will be outputting that. Okay. Now, so we need to prove this theorem, and that theorem implies the correctness of the algorithm. Okay. And this side, very easy. I already explained. Okay. Now let us prove this side. F hat I is greater than or equal to fi minus m by k plus 1. Okay. To prove that correctness, just visualize the algorithm in a different way. Okay. How do I visualize the algorithm? Assume that the numbers are like the elements in the array are like from the set 1, 2, 3 up to n, and I have n counters, c1, c2, etc. up to cn. Okay, and we are going to maintain, like we are going to keep k of these count, at most k of these counters non-zero, and the remaining will be zero all the time. Okay. Whenever the element, jth element aj comes, if the counter value in C of aj is greater than say 0, then you just increment that counter. Okay. And otherwise, suppose less than k counters among all the counters C1 to Cn, less than k of them are positive, then I just change C of aj to be 1. Okay, where aj equal to a of j. And if that is not the case, there are k counter values, everything like k counter values which are positive, and the aj is not, like C of aj is not there, then what you do is you decrement all the positive counters by 1. So essentially what you are doing is, like, you are going to forget about s, and like instead of that s, you use corresponding indices in the C counters. And whenever you are going to replace, whenever you are going to add something to s, which means that corresponding index counter will be incremented. Is the analogous notion clear? Like this is only to prove the correctness. So it is doing same as what we did before. So if you look into the previous algorithm, at any point in time, we have k counters d1, d2, etc. up to dk. They will be representing some elements which I call it I1, I2, etc. up to ik. So and that values will be stored in the counters C of I1, C of I2, etc. up to C of ik, and the remaining counters are 0. That's all. That is all the difference is. Is the algorithm clear? Do I need to explain it again? Like the alternate view of the algorithm? Okay, then let us prove the correctness. So we want to show this one, right? Fi minus Fi hat is less than or equal to m by k plus 1. Okay, and once we prove that, we are done, because this is what, like, so you just check Fi minus Fi hat is at most m by k plus 1. That is an equivalent statement of this one. And so to the analysis, always think this alternate view of the algorithm. You have n counters C1 to Cn, and exactly k of, at most k of them will be positive at any point in time. And if some element comes which has a positive counter, then you increment it. And if an element comes and there are less than k positive counters, corresponding counter you change it to 1. And if all the k positive counters are there and an element comes which is not corresponding to these k positive count, which is not correspond to any of these k positive counters, what you do is you decrement everything by 1, every counter by 1. Okay, like think about that alternative view. Now in every iteration, we are going to do the following operation, right? Either we are going to increment one counter, okay, some one counter, okay. So that is like already a positive counter, we may be incrementing by 1. Already one counter is not there, which means that counter value was 0, and then you are incrementing by 1. Like if there are less than k positive counter values, then you are going to increment one of the 0 to 1. So in an iteration, either you increment one counter, okay, that is one kind of iteration, and the other kind of iteration is like you are going to decrement k counters. In one iteration, you are going to decrement k positive counters. So that is another kind. Okay. Now, suppose look at the like categorize iteration. Like some iteration is an increment iteration, some iteration is a decrement iteration. Suppose there are L iteration which are decrement iteration. Okay, so how many total number of decrements you are happening? K counters you will be decrementing one each, right? And these K counters which you are going to decrement, that corresponds to K increment, K iteration which you incremented before. Okay, so which means that there are LK, then there are LK iteration which were incremented those counters, and there are this L iteration which is corresponding to the decrement counters. And how many number of iteration totally I have? I have M iteration, which actually means that the tot like M is at least LK plus L. L corresponds to the decrement iteration, and if I am doing a decrement in an iteration, for corresponding to one such iteration, I had made K other increment iterations. So which means that M is at least LK plus L. This means that L is at most M divided by K plus 1. Is that clear, that argument? L is the number of occurrences of decrement, number of decrement iterations. And then we can prove that L is at most M by K plus 1. Okay. Now, fix an element I want to prove this one. Fi minus Fi hat is at most M by K plus 1. Okay. Now, just substitute the value alpha to be Fi minus Fi hat, and you think that alpha is changing, like the array is there. Initially, you haven't seen any of the elements in the array. At that point, Fi is 0, Fi hat is 0. Fi hat value is actually the value Ci. Okay, that value is 0. So alpha is 0. When you keep going from left to right, the Fi is also changing and Fi hat is also changing. Fi hat is like what is stored in Ci. And at the end, what you get is actually Fi minus Fi hat. Okay. Now, so the alpha is changing when you move from left to right, like when you do iteration 1, 2, 3, etc. up to M. Okay. And initially alpha is 0. Okay. And initially I haven't seen any of the iteration, which means that L is also 0. L, you think it as a variable that counts the number of decrement iterations in the algorithm. Okay. Now look at how the L changes when you move from left to right, or in other words, when you are going to do this iteration from 1 to M. Okay. When look at the jth iteration, if Aj equal to I, and you have incremented the counter, then what happened? The Fi value incremented, Fi hat value also incremented, or alpha didn't change. Okay. Now, if Aj value is equal to I and Ci is not incremented, okay, what does it mean that Ci is not incremented? You decremented something, right? So that operation is a decrement operation. Then what happened? Ci value didn't change, but Fi value increased by 1. So alpha increased by 1. Fi value didn't, Fi increased by 1, Fi hat didn't increase because you made a decrement operation, like it is a decrement iteration. And so that you charge it to one of the decrement iteration, like that is, so you just change L to, you just say that, oh, I have came across one decrement iteration. Okay. Now the other case is Aj value is not equal to I and Ci value decremented. So a new Aj value came, and this a new Aj came, like that Aj is not equal to I, and then you are going to decrement all the counters, right? Then alpha increases by 1, right? So Fi hat decreases by 1, Fi didn't change, which means that alpha value increases by 1. And that iteration corresponds to a decrement iteration, right? You are going to change, you are going to decrease the counter values, which means that that is yet another decrement iteration. So at the end, what is the maximum number of decrement iteration I can have? That is what this says, L, which is at most m by k plus 1. And what is the maximum value alpha can have? The maximum value alpha can have is actually the maximum number of decrement iteration, which is actually m by k plus 1. And that's it. Like alpha increases at most L times, and L is at most m by k plus 1, and alpha is actually equal to this quantity, and hence I got this one. Is the proof clear? If you have any questions on this, then please ask. So we use a charging argument to prove it. To prove it. Okay, then I will stop here. And I hope you have seen the message. Today there is no tutorial. So we'll be seeing tomorrow then. Okay then, bye.
I have a question.